Okay, so let's look at in this particular discussion a very popular diode circuit called the Clamper circuit. And before we go into the details of how a clamper circuit works, let's try and understand what a clamper does here. So often we describe the operation of the clamper with respect to a sinusoidal voltage. As an example, we shown here a sinusoidal voltage with a peak amplitude of 3 volt. Now what a clamper does is that it clamps the output of the clamper is a modified voltage which is clamped. For example, in this case it is clamped at 1 volt here, meaning that the voltage cannot exceed 1 volt here. So as you can see here, that effectively what is happening here is that we have taken the input and we have shifted it by a certain magnitude such that the peak value does not exceed what we call as the clamping voltage here, right. So that's so although clamper will work with other waveforms also, so we commonly describe it using a sinusoidal wave here. And so remember that there is a clamping voltage called Vc. This is the voltage, for example, we don't want the output to exceed this particular voltage. Now there can be other clampers where we do not want the output voltage to fall below a certain value here. So the clamping voltage could be, for example, -1 or -2 or and so on and so forth. And this is what the circuit is supposed to do. Now often what happens is that we are given a circuit like this here. We are given a diode circuit of the kind that is shown over here, and then we analyze it and we try to show that it gives rise to a waveform of this particular kind, that it works like a clamper, that is able to shift the input waveform by a certain magnitude so that the output gets clamped at 1 volt here. So this is what we call as the analytical approach. We are given a solution, right? The solution is already given. So this is the problem, right? This is the problem that we want to solve, that from the input voltage given like this, we would like to arrive at an output voltage of this particular form. So that's the problem. And so what we often engage in is we are given a solution, and then we try to see how this solution is able to solve this particular problem here, right? And this is called the analytical approach. We analyze a circuit and try to find its behavior and confirm that it indeed does what the circuit is supposed to do. All right. An alternative approach is called the synthesis approach, where we start with the problem. We start with the problem and we try to construct the solution. We try to construct the solution in a step-by-step manner. And so that is another alternative way of studying, for example, circuits, and it gives you another perspective, and sometimes it helps you appreciate why the circuit is constructed in a particular manner. All right, so with that in mind, let's look at, in fact, the analytical approach to diode clamper circuit you will find in many textbooks. They would explain how the circuit over here works as a clamper. But in this particular discussion, let's look at the synthesis approach, how we may construct a solution like this here, this solution that we see here, in a step-by-step logical manner here. All right, so let's start with the basic problem. So we are starting from a problem and going towards the solution. So our goal is that, note that to clamp the voltage, if I want to clamp the voltage at, let's say, Vc, that's a clamping voltage, right? So this is the clamping voltage here, Vc. So we want to clamp the output voltage to Vc, and just for the sake of discussion, we'll take 1 volt. So effectively what it means is that the maximum of the output voltage is going to be Vc. So effectively what we have to do, effectively what we are doing is we are creating an output which is the input minus a shifting voltage here, some voltage by which we shift it down, right. So note that what we have to do is the input amplitude is 3 volt, and we don't want the maximum to exceed 1 volt, which means that the whole waveform we want to shift it by 2 volts here. So in this case, that's why Vb is equal to 2 volt here. So all that the clamper does is that it generates an output voltage which is equal to input minus a certain voltage by which it is shifted up or down. In this case, we are talking about shifting it down by a certain voltage. And how much voltage do we want it to shift down? Well, that's equal to the maximum of the input minus the clamping voltage. Note that the clamping voltage is fixed, let's say 1 volt. If the maximum of the input is 3, right, and so we need to shift it by 3 minus 1, 2 volt, such that the final output voltage will not exceed 1 volt here. If the maximum of the input voltage, was 4 volt, then we would need to shift it by 3 volt here. So if we shift it down by 3 volts, you can easily verify that the output will have a maximum value of 1 volt here, which is our clamping voltage here. So what we have to do then is basically note that the output voltage is very simple. The output voltage is simply equal to the input voltage minus a voltage by which we want to shift it down, and that voltage is equal to VIM minus VC, where VIM is the peak amplitude of the input voltage here. So this is what we want to do. We want to create a circuit which will do this, here, right? V0 equal to Vi minus Vb, such that Vb equal to VIM minus Vc here. So that's our task, to create a circuit which will do these two things here. All right. So how do we do it? Well, since we have to subtract a voltage, note that V0 equal to Vi minus Vb, and so we have to subtract a voltage. So it's very easy for us to say that if we have an input voltage Vi here, suppose we add a battery equal to Vb, and we put a load. Let's say this is the load resistor here. So the output has to appear across some load. So let's put some load resistor here. So we can clearly see that V0 equal to Vi minus Vb. So subtraction is straightforward that we need to. But there's a problem. The problem is that Vb equal to Vim minus Vc. So Vc is fixed. Let's say equal to 1 volt, the clamping voltage. But Vim will vary with the input. If I have a one particular input, let's say 5 volt sine omega t, then Vb equal to 5 minus 1 equal to 4. But now if I apply some other voltage here, 4 volt sine omega t, Vb will become 4 minus 1 equal to 3 volt. So we can't keep on changing the battery voltage here in response to changes in the input that is there here, right? So that's the problem. We cannot create a fixed battery here, a battery equal to Vb, because the value of Vb keeps on changing with the nature of the input here. And so what we want to look for is a solution. So this solution will work, but we have a problem that Vb varies with, the value of Vb varies with Vi, and we'll have to keep on changing the battery depending on the nature of the input here. So how do we solve that particular problem, right? We still want to subtract a voltage from Vi, but that voltage Vb can adapt to the value of Vi that is there here. All right, so that's what we are looking for. It can adapt, because Vb equal to Vim minus Vc. So how do we do that? All right, so suppose we don't really need a battery because we don't need a source of power. So suppose, and a battery is anyway not working. So suppose what we do is we take a capacitor. And what we do is by some means, suppose we charge the capacitor to this value here, Vim minus Vc. Right, so we take a capacitor which is charged to this value equal to Vim minus Vc, and then we connect it in this particular form with a load resistor RL here, and we make sure that the time constant RLC is much larger than T, so the capacitor will not get discharged, okay, and will neither get charged nor discharged because the time constant is very large compared to the time period here. So this should work. Right? We don't really need a battery. We take a capacitor and we charge it to this value here, Vim minus Vc, and then this will work because the time constant is so large. So what will happen is that output voltage will again be equal to Vi minus Vb. Note that the capacitor will not charge or discharge, so the value across the capacitor will remain fixed, the fixed voltage which is equal to this value here. which is equal to this value here, right? So a capacitor will also work provided we are able to charge it to this value here. We are able to charge it to this value here. So the question is now, how do we charge a capacitor to a value equal to VIM minus VC? I mean, it doesn't make sense that you take a capacitor, separately charge it to this particular value and then put it in this particular circuit. So we can't do that. That would be too inconvenient. So we want to look for a way of modifying the circuit so that the capacitor automatically gets charged to that particular value. All right, so how do we do that? So suppose I take this capacitor here and I add a voltage VC. VC is my clamping voltage. So what will happen is, let's see what happens. So let's suppose the capacitor is initially not charged. So Vi, let's say from here, let's focus on the waveform here. So Vi starts increasing. Vi starts increasing, and what happens is the capacitor here will begin to get charged, right? So there is a path here. Note that the RL doesn't charge, this RL does not charge or discharge the capacitor here. We've already chosen A2 large. So it charges, for example, through this path here, right? So it will keep on charging. It will keep on charging like this till the input reaches a value VIM. So there will be a point where this value input will reach VIM, this node, and this node is anyway VC. So at that point, the voltage across the capacitor is VIM minus VC, which is what we want. But then what happens is Vi will decrease after that. And as Vi decreases after that, then this voltage will change here, this voltage will change here, and the capacitor will discharge. Right? So what we want is that the capacitor, we want the capacitor to charge till a point VIM equal to VC, charge up to that value here when the voltage at this particular node reaches equal to VIM. But after that, it should not, the capacitor should not discharge. And note that the discharge path is like this here, right? It discharges like this here. Because after charging to a maximum value of VIM minus VC, the capacitor would begin to discharge, because this voltage at this particular node is falling and this voltage node is unchanged, right? So we would like to prevent the capacitor from discharging once the voltage at this node here reaches equal to VIM. So how do we do that? Well, suppose we put a switch here. So what we do is the switch is closed initially. The switch is closed, and so the capacitor charges, keeps on charging till I reach the maximum point here, VIM. And just when it reaches the maximum point VIM here, I open the switch here. I open the switch. Now what would happen is the switch is open, and the voltage across the capacitor would become VIM minus VC. Right? And we have achieved our objective. So we wanted VB equal to, we wanted a capacitor to be charged equal to VIM minus VC, and we have done that. So the switch is initially closed. We allow the capacitor to charge till this node reaches the maximum value. The moment this node falls below VIM, we don't want the capacitor to discharge like this, right? And we open the switch. Right? We open the switch, and then we have achieved our solution. But how do we implement the switch here? How do we implement the switch? Right? And note that what we want is the switch should be closed till the input reaches its peak value, and just after it falls below the peak value, we should open the switch. So we can't be sitting there opening and closing the switch, right? So we have to do it not manually, but electronically, right? So how do we create this particular switch? So note what the purpose of the switch is. The switch should be closed as long as the capacitor is charging, which means the current is flowing in this direction. Once this voltage reaches VIM, what happens is after that, the capacitor begins to discharge. The capacitor begins to discharge. And we have to prevent the current flow in this opposite direction here. So note what the switch is, what we have to do. The switch will allow, is basically allowing current to flow in this direction, right? It's allowing and is preventing the current to flow in the opposite direction here, in this direction here, right? That's what the switch is doing, because after it reaches its maximum value, we open it. So effectively, the switch is allowing current to flow in one direction and not allowing current to flow in the opposite direction here. So we see that the switch that we have is basically functioning like a diode. So what we can do is we can take the switch out and put a diode here. So now the diode acts like a switch. So as long as the capacitor is charging, the diode is on, and the moment this value reaches VIM, after that, the capacitor can only discharge, but the diode will prevent any current from flowing here and prevents it from getting discharged. And therefore, the capacitor gets charged to this maximum value VIM minus VC. And once it reaches there, the capacitor then remains at that particular value. Right? So that's how we arrive at this final circuit here. And so what we have done is note that in this synthesis approach, we started from a very simple solution like this here, solution number 1, and we gradually we saw that all we needed to do was V0 is nothing but Vi minus Vb.